Yes, done. Kindly proceed.
Okay. So should we start?
Thanks. Thanks, sir. Shall we start?
Yes.
Yeah, maybe.
Yeah. Now it's 3 past 6. Yeah, we could start.
Yeah.
Another
Okay.
5 minutes more introduction. By the time I think we'll reach 50 marks.
Yeah.
Okay.
Okay. So good afternoon, everyone. Welcome to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly hosted by South Asian Meteorological Association SAMA and Savitribai Phule Pune University SPPU. We are on the second last lecture of this series, and it will be delivered by Professor Dr. Anandakumar Karipot, who is visiting faculty here in SPPU, and he was also head Department of Atmospheric and Space Science previously. Before we proceed with the lecture, I would request Professor Someshwar Das sir, who is Secretary SAMA, to please give welcome address.
Okay. Thank you very much, Dr. Rohini. It's always a pleasure to welcome Professor Anandakumar Karipot. And then as Dr. Rohini has already said that this is the last but one lecture. And I'm sure that most of you who are regularly attending this lecture series has also attended his last lecture on the turbulence boundary layer, planetary boundary layer. And also, if you recall, the very first inaugural lecture was given by probably Professor Sen, was also related to boundary layer, the dispersal of the pollutants, if you remember correctly. So now it is more in elaborate, and earlier mentioned that boundary layer is so important for every aspect of the atmosphere. For example, if the boundary layer is stable, then convections cannot develop. If boundary layer is stable, then fogs cannot form. I mean, fogs can form rather in the stable boundary layer. If it is unstable, then fogs cannot form. And turbulence is so important in the boundary layer because it is the turbulent fluxes which mixes of the lower atmospheric characteristics or properties with the upper atmosphere. So Professor Anand Kumar is going to talk on these topics, very important topics, which are quite complex, but I'm sure that with his experience, he will make it so simple to understand to all of you, because all of you are from different backgrounds, ranging from Bachelor of Science to the PhD, and then also working professionals, and also probably some of the participants maybe from non-scientific backgrounds as well, just working on the climate science, and got attracted to this lecture series on atmospheric dynamics because of its applications to the climate sciences. So for all those participants, I hope that you have attended all lectures previously and tried to understand the concept behind the atmospheric dynamics. As all the lectures are available on the YouTube channel of SAMA. So it is always advantageous for all the participants who want to watch the previous lectures again and again and again, and then try to understand the concept. So with this, I welcome you once again on behalf of the South Asian Meteorological Association as well as the Savitribai Phule Pune University. So thank you, and on to you, Dr. Rohini.
Thank you, sir. I request Anand sir to please continue. The floor is yours.
Thank you. Good afternoon, all, and thank you, Professor Someshwar Das, Dr. Rohini, and SAMA. So this is the second lecture on boundary layer meteorology, which I'm going to deliver today. So it will be a we discussed many of the basic aspects in my last lecture, and today's lecture also mostly basic, but a little more advanced than the last day's lecture. I think today also I will have to go a little bit fast, so much to cover, but you can always, when you get the lecture slides, you can go through it and Also, after the lecture is over, if something is not clear, you can ask me the doubts as well. So one of the topic we will be discussing today is regarding the conservation equations in the boundary layer. Related to that, we need to make use of an approximation which is called the Boussinesq approximation. So first I will discuss that. So basically this, we can define a Boussinesq flow. So in which density variations are significant to cause buoyancy driven motion. That means the density fluctuations we allow so that the equations take care of the vertical motion, the fluctuations, but otherwise we ignore them. So basically what we do is that we assume that the density is constant. We assign a mean value to the density, except when it is contributing directly to the buoyancy. So where it is contributing to the buoyancy, we allow for the fluctuations. Otherwise, we just assume it as a constant density. The reason is that if we ignore the density fluctuations totally, then we will not be able to account for all this convection, the vertical motions that are taking place in the boundary layer. So when we say density is constant, that implies that the atmosphere we are considering is incompressible, and the local density variations which we allow in the vertical component of momentum equation. So they are basically the small perturbations from the basic state density field. So so we say that this is the approximation we want to use, but then we need to justify also. So when it comes to the boundary layer, so usually when we say boundary layer, it is of compared to the whole atmosphere or the whole troposphere, the thickness of the boundary layer is small, and most of the time it is turbulent, mostly well mixed. So we can say that in this boundary layer, the density is nearly constant. So variations can be within 10%. So this approximation is valid to a good extent. And then when you talk about the vertical displacement of the air parcels and all that, it may be going like within this boundary layer. So shallow boundary layer depth. So we can apply this Boussinesq approximation when we deal with the equations. So so it is usually coupled with the gravity, and then one of the conditions is that the vertical scale should be less than the atmospheric scale height. And with the help of this approximation, we can simplify the conservation equation. So with that background about the Boussinesq approximation, so we move on to the conservation equations in the boundary layer. So in your dynamic meteorology lectures, already you have learned about the conservation equations, the 6 of, if you include the conservation of water vapor, 7 equations, including the equation of state. So so why don't we use those equations as it is in the boundary layer, because that boundary layer is also part of the atmosphere, part of the troposphere. So one could ask why we modify or think about these equations, especially in the boundary layer. The main reason is that the boundary layer is almost always turbulent. So, and all these turbulent exchanges are very significant. So whereas our original conservation equations doesn't include all these turbulent motions and turbulent fluxes and these exchanges. So to represent what all going on in the boundary layer, so if our interest is to study the boundary layer is in detail, then we have to take care of all these turbulent exchange. So we need to modify our original conservation equations. So we can roughly go through these steps mentioned here to get the conservation equation. So identify the governing equations we want to deal with, and also we need to simplify with the help of this Bose-Einstein approximation, where we assume that the density is constant except in the vertical component of momentum equation. And then we discussed about certain tools like the Reynolds decomposition, where all the variables in the boundary layer we can split into the mean and the turbulent parts. We do that, and then we also apply the Reynolds averaging rules to get time averaged or space averaged terms. So begin with the three components of the momentum conservation equations in a simple form given here. Acceleration UV or in UV and W components, and what all contributes to it on the right hand side. So now we take these equations and first apply the Bose-Einstein approximation. So the first in the first two equations, the horizontal component equations, so we can assume that the density is constant. So we replace the density with rho 0 in those two equations. But we want to allow for the density fluctuations in the vertical component equation. So there we consider that the pressure equal to a level averaged pressure plus the deviation from that base state value. And similarly for the density, mean density, and then the deviation from that mean value at that particular level. And we also require that base state pressure and density satisfies the hydrostatic relation. And now I don't want to go through all the details of derivation. So we take the right-hand side of the vertical component of momentum equations, and then we apply this the deviation in pressure and density from the base state. Rho we write as rho 0 plus rho prime, and P as P for plus P prime, and then expand the terms, and then we arrive at this particular equation for the acceleration of vertical velocity. So here we see that there is a term, the second term on the right hand side says minus rho prime by rho 0. So this accounts for that density fluctuations, and then it says that the density fluctuation rho prime is positive. That means the air is heavy, and then what we expect is the negative buoyancy. So here there is a negative sign already, so this becomes this remains density fluctuation positive. So that means the negative buoyancy that way. But there is one difficulty here. So this term is rho prime by rho 0. Usually we don't deal with the fluctuations in the density directly for several reasons. And then so it will be convenient if we convert this term in a more user-friendly way. So if we can convert this term in terms of the potential temperature instead of density deviations, we can express that in terms of the potential temperature deviations. And so we rewrite the equation in this particular form. How do we convert this term into in terms of the potential temperature deviation is explained in the next slide, which you can go through if interested. So according to this equation, now positive temperature perturbation, that means the warmer air, so that creates positive buoyancy. So that way we can explain the physics as well. So this slide has all those details how we are converting from this term from rho prime by rho 0 to theta prime by theta 0. And then other equations. So the three equations we modified applying the Bose-Einstein approximation. The thermodynamic energy equation in a simplified form. The original equation we are familiar with is in this form, but in terms of potential temperature, we can write in this form, the derivative of theta d theta by dt equals the heat source or sink term, and that we can use as it is for now. And then the continuity equation dealing with the mass conservation. So this is the original equation, but here we are assuming that the density is constant. So the term, the left hand, the density variation with the time disappears, and the continuity equation we use will be in this particular form. And now to convert this equation, which includes the fluxes. So there are certain steps involved. So we make use of the total derivative of the acceleration, for example, and then split that into the local derivative and the advection term. And then, so we do certain rearrangement of the terms, and we get this particular equation. Here, for each of these variables, for example, u, v, and w, we apply the Reynolds decomposition. Each of them we write as u bar plus u prime, v as v bar plus v prime, and w as w bar plus w prime. And then apply the averaging rules, and then we arrive at this particular equation. So the total derivative, which is there on the left-hand side of the momentum component equation. So here we are explaining the u component. So that we have converted into this particular form. And again, making use of the continuity equation, we rewrite the equation in this particular form. And then other terms we have already there. Then we are getting the modified equation, the momentum component equations in the modified form. We get in this particular form. So many additional terms you see here. We will come back to this bit later. And the thermodynamic energy equation, applying that the same procedure, that Reynolds decomposition and averaging. And then we get into this particular form. Here also we see that there are so many additional terms, mass continuity equation anyway. So here we no additional terms here, just the mean of those three variables, u, v, w. And if you are using the water vapor conservation also, so then the modified equation will be in this particular form. So, so now we have got this set of modified equations, which are known as the Reynolds average equation for the mean state variables in the boundary layer, for the u, v, w, potential temperature, and the moisture. So all of those we can bring together all the equations, and we can add the equation of state also. So totally we'll be having 7 equations. But if you look at these equations, so originally all these terms were not there. So our original conservation equations, for example, the momentum equations, we have only these terms, and of course the friction. But now we see that there are so many terms in this square bracket with all of these equations. So many additional terms have appeared in this equation. So we know that this product of, for example, w prime u prime, or w prime q prime, or w prime theta prime, they basically represent the fluxes. In the last class, we already discussed the concept of Eddy fluxes. So where we discussed that mechanism and showed that this covariance between the flow and the quantity of interest gives us the flux. And the covariance will be basically the product of the fluctuations, the product of the fluctuations in the flow and the quantity of interest. Heat flux is, for example, w prime theta prime, momentum flux w prime u prime, like that. So the terms what we see in the square bracket, the additional terms that appear in these equations are basically the gradients of the fluxes. Not the fluxes as it is, but you see that whether either horizontal gradient or the the vertical gradients of all those fluxes have appeared in this equation. So that's how we are introducing the turbulent exchange in these equations. Well and good. So now these equations are in a way ready to use for boundary layer studies. But it's not that easy as we may think, because to solve these equations, one requirement is that the number of unknowns or the variables or dependent variables should be equal to the number of equations. So when we had our original equations, 7 equations, we had 7 variables: UVW, density, pressure, potential, temperature, and the mixing ratio. So we balanced the number of unknown variables and the number of equations, 7 and 7. So we are fine with that. So we could solve the equations. But now we have modified the equations, including the turbulent exchange in the form of this flux gradient. But now we see that all these additional terms. So these are actually, we don't know the values of this. These are unknowns actually. They are dependent variables. The fluxes, all these fluxes, W prime, U prime, or W prime, Q prime, or W prime, theta prime, all these fluxes and the gradients are unknowns. So that means the number of unknown terms have increased, unknown variables have increased, but the number of equations remain the same. So that is the problem now we have to face. How do we solve this? So this particular problem is called the closure problem. The number of dependent variables or unknowns are now more than the number of equations, so which we call it as the closure problems, and these additional terms are the flux gradient terms. So one way to solve or come out of this situation is that try to increase the number of equations. We can write the additional equations for the flux, for example, U prime W prime, or its gradient, dou by dou Z of U prime W prime. So we write one additional equation. But what will happen is that if you do that, there will be higher order unknowns appearing in those equations. Again, in the gradient form, the terms, the gradients of U prime, V prime, W prime may appear in those equations, or W prime, theta prime may appear. And then, of course, we can write additional equations for those higher moments also, but it will be a never-ending process. And again, it's not just writing the equations, and the one purpose of doing this is to solve and use it in the numerical models. But then if you write additional equations, we have to feed the models. We have to provide the input. But we don't have measurements of all these fluxes. Even the fluxes itself we don't have. Then where do we have all the values for higher moments to feed the model? So we don't have. So we cannot keep on adding the equations. And again, if you keep on adding the equations, we solving also, the computational requirements also increases. So that's not the way. Keep on adding the equations to make the number of unknowns and the number of equations match. It's not going to solve our problem. So what we do is that we decide somewhere we have to compromise. We say that, okay, we cannot go beyond certain number of unknowns, number of these flux terms or the flux gradient terms. So we can decide, okay, we will keep U prime, W prime, or we keep W prime, theta prime. But beyond that, when it comes to like a W prime, theta prime, we don't go for it. For that, we approximate that way. So that way we decide and approximate the higher moments or wherever we want. And then with the help of such an approximation procedure, we can try to make a complete set of equations. A closed set of equations we can say, and then we can solve them. So I'll quickly go through some of the procedure steps we follow usually, the closure, the schemes. So that they are named basically based on, there are 2 ways, based on the order of statistical moments we keep in the equations. And then also based on how do we, whether we use the local gradients to approximate, or we use the a larger domain to approximate all these fluxes. So statistical moments, there are different orders of statistical moment. First moment means there's the variables as it is. And second moment means the fluxes like U prime, W prime, theta prime. There are second moments and third moments like U prime, V prime, W prime, like that. So the order of closure, so naming is like if it is zero order, that means all terms, we don't even keep UV, W, theta, there itself we approximate. So, so that means there will not be any prognostic or diagnostic equations for these variables. So original equation itself, we will represent using some empirical formulations. And then first order closure, that means we will have all these first statistical moments in the equations, but we will approximate this using the first moments. And then if it is second order closure, then we will be having all these flux and flux irradiance. Second moments we will keep in the equations, but all these third moments onwards we will approximate. So that's how the naming based on the order. And then local or non-local. So these fluxes, you will see in the coming slides that this fluxes we can approximate in terms of their gradients. So these gradients we can calculate in different ways. Either we can use a local gradient, means between two levels, say 10 meter and 20 meter. Between these two levels, you can calculate the gradients, and then the fluxes we can express in terms of those local gradients. So that is, if we are doing that, then we can call it as a local closure. That means we are using the information just from those two levels. It may work sometimes, but not necessarily always. And then it works if the turbulence is weak and the eddy sizes are small, but and then the exchange is according to as per the gradient. But the turbulence means it is chaotic, random, chaotic. So we should expect counter gradient fluxes also against the gradient. But then if you use the local closure, then local gradients, then it will not account for the counter gradient fluxes. So then the other ways that use the non-local closure. So here, instead of just those two levels, from a larger domain, the information available is used to calculate those fluxes. And then the naming convention. So basically combination of both the order and the local or non-local. So the naming will be like first order local closure, first order non-local closure, and 1.5 order. Sometimes there will be some of the first moments and some of the second moments we may keep. Then we call it as 1.5 order local closure, like that. So then what we should be choosing? We have a choice. Okay, it is better to go for higher order, like second order closure or third order closure, and the non-local. So non-local and higher orders are preferred, provided several aspects. So if we have the input to provide of these fluxes and all that, and then we have the computational power to solve all the additional number of equations, and also we can take care of all these numerical solving issues that may also arise. So if that is all possible, then it is better to go for higher order and non-local schemes to solve the equation. Just we can try to explain that with just a simple closure scheme, which is the first order local closure, also known as the K theory. So here, local, the fluxes will be calculated from the local gradients of the variables UV, W, theta. So we are here to explain this. We are just using the two horizontal momentum equation and that thermodynamic energy equation. So the flux gradients are coming here. So these are the additional terms what we have now, all these gradients of fluxes. So what we do is that we assume that the gradients decides the turbulent flux. So, the gradient of a quantity determines the turbulent flux. So then we write in general, the flux we write in terms of the gradient of that quantity multiplied by a coefficient is basically a scalar with the units meter square per second, having different names: eddy viscosity coefficient, eddy transfer coefficient, turbulent transfer coefficient, gradient transfer coefficient, like that. So this is in the general form, but remember that this coefficient k is not constant. It varies based on the flow properties. So an example. So for example, if you want the momentum flux U prime W prime, so we can write that in terms of the eddy transfer coefficient Km, and as the gradient of the wind dou U by dou Z. So we just take the local gradient of the wind component, U component, and multiply that with this eddy transfer coefficient, and we consider that as the flux. So with this type of, so here we are actually approximating. So the flux we are approximating in terms of this gradient, and like that, all the different flux terms, the other component of momentum flux and the vertical heat flux. So all that we can express in terms of the corresponding gradients and put back in our equations. So we see that all those flux terms of the gradients of fluxes have disappeared. Now we are writing those in terms of the mean variable. So we we don't see any additional unknowns. So that means we can solve the equation. But remember that we are doing with the help of approximation. The fluxes we are representing in terms of the corresponding gradients. So that way, all these fluxes, for example, momentum flux in the original form minus rho U prime W prime. So that we are writing the eddy transfer coefficient for momentum Km multiplied by density and the local gradient of the U component in the vertical, and sensible heat flux. So this is a direct way using that eddy flux concept, rho Cp W prime, theta prime or T prime. And using this K theory, we write in this form, and similarly the latent heat flux. So this is basically the flux gradient method. So we are expressing the fluxes in terms of the gradients of those variables. So for the K, the momentum, heat, and latent heat, the transfer coefficients are different, and near neutral conditions from the experiments and all that, people have found that this relation KH is nearly equal to KQ, and but it has to be multiplied with 1.35 to get the KH and K with respect to K. And this K theory has several limitations. So K is flow dependent, so we cannot assume that it's a constant. Calculating the value of this is not that easy. So, but if you assume K is constant, the value of K may varies in a very large range, starting from 10 raised to minus 2 to 10 raised to 2 even in some of the flow conditions. So highly variable depending on the flow condition, depending on the turbulent nature. So we cannot assume that it's a constant. So determining that is not that easy and to use in these equations. And then this eddies that cause are not necessarily small in size. Many of them will be very large. And then if you use these local gradients to calculate the fluxes, it may not be making sense. There will be counter gradients contributing to the fluxes, which we will not be incorporating here. So all that matters. So K theory is not a foolproof way of approximating or closing the equations, but very often people use this approximation for various reasons: computational requirement, absence of input data, things like that. And then how do we calculate Km? Briefly mentioned here using the mixing length theory. I think this will be explained by Professor C.A. Babu in the next lecture. The mixing length theory, the Km we can write as L square absolute of this gradient of the U component. L is the mixing length, which is given by Kz, and this is the small k von Karman constant. It is having a value of 0.4, and Z is the measurement height. So this way, using this relation for near neutral conditions, we can calculate the value of Km and use in those previous equations, provided the atmosphere is, or the boundary layer is neutral and the local gradients of measurements are available. So now it's not actually mentioned in the syllabus of this lecture, but to explain the stability, I will quickly go through this TKE, turbulent kinetic energy. Briefly mentioned it in the last class also. So we can calculate the turbulent kinetic energy from the fluctuations of U, V, and W components in this equation like this. So, and actually it is a measure of the turbulence intensity, and there are various other applications. So people always, to study the boundary layer and its evolution, people often look at the TK budget. That means E represents that TK in this equation. How the TKE changes with the time. What all contributes to the change in turbulent kinetic energy. That means what all contributes to the variation in the turbulence itself. TKE represents the turbulence intensity. So there are various terms you see on the right-hand side. So the adduction, the TKE itself may get adducted by the mean wind from one location to the other. One location may be more turbulent for whatever reason, and somewhere else it may be not that turbulence. So it is possible that the mean wind adducts the turbulence itself horizontally, and that can contribute to the local change. And the buoyancy effect, the up and down motions due to the thermally generated turbulence. This term actually represents both the generation as well as the consumption of the turbulence. And the shear always generates the turbulence. The variation of wind with the height due to the friction and the viscosity effects, there will be almost always friction in the wind. So shear in the wind, and that can contribute to the turbulence generation. So these two terms basically represents the turbulent production, and this during stable condition, this represents the consumption also. And then the turbulence can get transported within the boundary layer from one level to the other vertically also. So vertical flux of TKE itself. So that also can contribute to the local change. And then the pressure fluctuations associated with some of the wave motions, that also can contribute to the local change. And dissipation. The turbulence also gets dissipated when they lose the energy and get dissipated in the form of heat. So all that, so with the help of this equation, we will be able to say how the TKE is going to change with respect to time. But remember that these two equations, these two terms, the buoyancy term and the shear term, basically decides the turbulent nature, or how the turbulence is going to change with respect to time. So making use of all those are mentioned here, so you can go through this in detail to know more about it. So now, basically, I want to explain the boundary layer stability with the help of those two terms in the TKE budget equation. So we are all familiar with the static stability or instability of the atmosphere in general. So basically, when you look at the static stability, it is measure the capability for buoyant convection. So there we are not looking at the effect of wind or turbulence explicitly. So, and then if air is statically unstable, so that means the air will be less dense than the surroundings, and it will rise, and the other way it will sink if it is the other way. So, and usually we determine this static stability of the atmosphere using the dry adiabatic and the environmental lab state, which is represented here in this schematics. But then, so okay, this gives the basic information in the boundary layer also, but then that's not really good enough in the boundary layer. So we need to go into a little more detail, because most of the time our interest is to know also whether the boundary layer is turbulent, weakly turbulent, or not turbulence at all. So to get all those details, that static stability information, just knowing statically stable, unstable, or neutral alone will not help. So we need to look into a little more details. So, so daytime, we know that most of the daytimes, if it is sunny, hot conditions, so usually it is statically unstable. So usually we see that convectively generated turbulence will be there, and there will be a lot of turbulent mixing. So dynamically unstable. From point of view of turbulence, we can say that such situations, statically unstable will be dynamically unstable. But nighttime situations, we have a difficult or more complex situation. Stable in nature, that means statically stable, but doesn't mean that not turbulence. Statically stable doesn't mean that always not turbulence. That also I showed some actual scenarios. Night times can be turbulent, weakly turbulent, intermittently turbulent, all that situations are there. So stable conditions can be turbulent, can be weakly turbulent, or can be not turbulent. So for that, we need to make use of additional measures of stability. So from that we can do, you making use of that TK budget equation, just make use of those two terms, the buoyancy term and the shear term, and calculate certain parameters called the, I'm just talking about one of the Richardson number here. This is called the gradient Richardson number, represented as Ri, as given by this formula. Basically, the ratio of the potential temperature gradient and the square of the shear. So actually, in those equations, we saw that in the flux form. So there we can, those fluxes we can express in terms of their gradient using the K theory. And then that's how we are getting this Richardson number. So basically, this is the ratio between the buoyancy term and the shear term in the TK budget equation. So based on the sign and the value of this Richardson number, we can we'll be able to judge what's the nature of this boundary layer in terms of the dynamic nature of the boundary layer. So negative, if you get a negative value for this Richardson number, that means it is unstable situations. That means potential temperature is decreasing with the height. So unstable. So dynamically, usually unstable situations are dynamically unstable. That means it is turbulent. But then if you get a positive value, that means theta and temperature increasing with the height, you get a positive value for Richardson number. But then whether it is turbulent or not, so that depends on what value we are getting when you calculate the Richardson number. And we will have to compare with two critical values. One is RC, we call the critical Richardson number, and there is another critical number which is called RT, the termination Richardson number. So depending on the magnitude of the Richardson number you are getting, and initially what kind of a flow is existing. So assume that the condition initially is laminar. So then we want to make use of this Richardson number and see when it is, whether it may become unstable, whether it may become turbulent or not. So initially, if it is laminar, then it may become unstable, and we can expect the onset of turbulence when the Ri values you are getting becomes less than Rc. Means the values of Rc from the experiments people have found it in this range, close to 0.2. So the value you are getting, if it is becoming gradually, it may become less than this 0.2, then we can say that the laminar flow will become turbulent. And if it is existing situation is turbulent, and you want to know whether with the time it is going to become laminar, and then the values you are getting, calculating, you will have to compare with the values of the termination Richardson number, which is having a value of 1. And if it is exceeding the Richardson number you are calculating, if it is exceeding the RT, then that will indicate that the flow, initially it was turbulent, but now it would have become laminar. So that way, based on the values of the Richardson number we are calculating and what is the initial situation, we will be able to judge whether it is going to change from laminar to turbulent or turbulent to laminar. One example is shown here. The calculated Richardson number is shown here, and then the vertical velocity fluctuation. So you can see that during daytime, Richardson number negative, indicating unstable conditions. So it's quite turbulent. And but then evening hours, because the time also, the Richardson number has become positive, but it remains less than. Originally, it is turbulent. So here and all that the value has become 0.5 positive, but still it is kind of moderately turbulent. So it will continue to be turbulent until the Richardson number crosses that terminal value, RT. RT is 1. So here it has crossed, and then you see that the Richardson number, the turbulence has become very, very weak, and it continued to be weak because it didn't go below 0.2. So here it has become nearly laminar, and for this to become turbulent again, should go below the critical Richardson value 0.2. It does not happen. So you see that here it is laminar again. So that way we can make use of the Richardson number, and there are other Richardson number called the bulk Richardson number. So for gradient Richardson number, you need to have the measurements of the gradients in the temperature as well as the wind speed, local gradients. But we may not be having that always with the measurements as well as in the numerical models. And then because, for example, if you are using radio sound observations, we don't have very closely spaced observations. Or one observation may be at 10 meter and the next one may be at 200 meters. So we cannot use those to calculate the local gradient. So in that case, we make use of the bulk gradients and then calculate the Richardson number. So that is the bulk Richardson number. And there is yet another measure of the stability, which is called the Obuco length, represented by capital L here. That again is the ratio between the shear term and the buoyancy term in the TK budget equation. The interpretation is slightly different. So if you calculate and get a value, so this is the length actually, Obuco length, we express that in terms of the meter. The unit remains as of that of displacement itself. So if you get a value for L in terms of say 20 meter, so what does it mean? So, and then you need to always relate to the measurement height. So for a particular observation height, if the value of L you are getting is much more than Z, then up to that height. So the way we have to interpret is that L is the height above the surface at which buoyant production at first dominates. So if you get a value of L equal to 10 meter, so above 10 meter, the buoyancy effect is dominating in generating turbulence, and below 10 meter, the shear effect is dominating. So buoyancy effect dominating more closer to the surface means it is going to be highly turbulent, because buoyancy generated turbulence is usually stronger than the shear generated turbulence. So if you get a small value for L, negative means again unstable. A small value for L, that means from closer to the surface itself, the buoyancy generated turbulence is there. So that way we can interpret the turbulent nature of the boundary layer. Not going in all the details, but here it is related. Always we'll have to relate to the measurement height. With respect to the measurement height, the value of L, then we'll have to judge. So to remove that dependency on measurement height, we can normalize with the height of measurement and define another parameter called the stability parameter used in the surface layer, Z by L. And we can use it directly without referring to the measurement height. And so now coming back to the different flux measurement or estimation methods, there are several methods one can use to calculate or estimate. So which are, I have mentioned 2-3 of them here. The Eddy covariance method, which is basically a measurement method, direct method, and then the flux gradient and bulk aerodynamic method. These two are, using these two methods, we will be actually estimating. We will be using some coefficients, some empirical relationships here. So basically we are estimating using flux gradient and the bulk aerodynamic method, whereas Eddy covariance is actually a direct measurement method. We already mentioned that all these fluxes we can express in terms of the covariance between two variables. Our interest is in the vertical fluxes. So W prime T prime or W prime Q prime or W prime U prime gives the sensible heat, latent heat, and the momentum fluxes. And you multiply with the Cp rho, you get the actual fluxes in watts per meter square. And so this is how do we arrive at those formulas are mentioned here. Basically, the covariance between the flow and the variable of interest. And then we explained this eddy flux concept in the last class. That's how we are getting those fluxes. And actually, what is happening with the help of the schematic, it shows what is happening in the boundary layer. So all kinds of motions, random, irregular motions up and down, and rotating motions are there. So mixing is taking place, turbulent eddy is going up and down, and then using that eddy flux concept, we arrive at those formula. And so these fluxes are having the in all the three directions, and so we can get those. And this eddy covariance has, though it is a direct method, there are several assumptions I have listed here. We don't have time to go through all this in detail. So, so we will get this direct method will give us accurate results if all this all these assumptions are met. What we are relying on is met, then we will get correct values of those fluxes. Otherwise, here also we should expect a lot of errors. And yeah, usually this eddy covariance method we use to calculate fluxes from the measurements. The numerical models, we don't resolve the eddies usually in normal models. In large eddy simulation, yes, but those are a special category of models. But in usual numerical models, we don't resolve eddies, so we don't calculate those fluxes using eddy covariance in the numerical model. So usually it is a measurement-based method. So eddy covariance method we can use. A typical measurement setup is shown here. We need to measure all the three components of the wind using a three-dimensional fast sonic anemometer. And then we need to have the other quantity of interest like the, and sonic anemometer gives us the sonic temperature or virtual temperature. So that gives the temperature fluctuation as well. And then if you want to calculate the latent heat flux, we need to measure the mixing ratio also at a fast rate like 10 times a second or 20 times a second. So these are very specialized instruments which are capable of measuring the wind components, the virtual temperature, and the concentration of gases like water vapor or CO2 at a very high frequency, like 20 times a second, 30 times a second. So from that, we can get the fluctuations, and from that, we can calculate the covariance and get those fluxes directly. And different types of setups, sometimes you may need only at a single level, sometimes depending on what you are trying to study, there may be a tower of 50 meter or 100 meter, and then you can set up this at a different levels and calculate these fluxes. This is how the raw data may look like. The components U, V, W, U, and W are shown here, just the random fluctuations, temperature may look. Everything looks very messy here. The concentration of CO2, that's how it looked, the raw data, but then if you look closely, put W and the temperature together, you see that there is some disorder. It's not totally messy. When the air is going in the vertical direction, during the daytime, the temperature also going up slightly. So the lower part of the surface is warmer than the air above during daytime. So air going up takes warmer air up. So air temperature is also increasing. So it makes sense. So the previous here, when you look at it, it looks totally messy, but here it makes sense. So when you calculate the covariance, you get the fluxes. And if you calculate, for example, during the course of a diurnal variation of the fluxes using the eddy covariance method, the sensible heat and latent heat is shown here, how it varies. It may vary like this, and converting into the flux watts per meter square. So it may look like this. The magnitude may look like this, depending on the type of the atmospheric as well as surface conditions. So this is like a mostly dry situation. Sensible heat flux is much more than the latent heat flux. Just to give you some idea how it may look like. And then there are several problems. Direct measurement doesn't mean that it is perfect. The assumptions are met, then we may get correct results. Otherwise, there can be a lot of issues. And those two estimation methods, flux gradient and bulk aerodynamic relations. So these are basically, so eddy covariance means we are directly calculating, measuring the fluxes from the fast high frequency measurements. And we know that it's not always available. Numerical models doesn't simulate at all, except the large eddy or DNS, direct numerical simulation. So, and in the measurement itself, normal weather observations, what we do, we are only measuring the mean quantities of temperature, relative humidity, and the wind speed, like that. So, and the numerical models also simulate the mean quantities only at different levels in the atmosphere. So we should have some way to estimate those fluxes in the either in the numerical models, or if the high frequency measurements are not available, then we will have to calculate or estimate it from whatever observations are available. So these two methods are basically meant for that. Approximations are involved, so naturally there will be more errors, specifically because those coefficients involved. Already we explained that flux gradient method, the K coefficient, the values of that, calculating that is not that straightforward. So there will be errors associated with that. So basically the flux gradient relation relates the fluxes to their gradients, whereas the bulk aerodynamic formula relies on this flux gradient relations, but flux gradient requires the local gradients. And okay, we are doing measurements. It may be possible to do the measurements at two heights, maybe like 2 meter and 10 meter above the surface, and calculate the local gradient and using that flux gradient relation. But and the numerical models, such local gradients may not be available. At fine resolution, numerical models will not be having. Okay, you may have a value close to surface, maybe 2 meter or 10 meter, and the next measurement maybe next level maybe at say 100 meter or 200 meter, or the spacing of say 25 hectopascal, like that. So local gradients are not available in most of the numerical models. So we need to rely on whatever is available at the surface values, and at the whatever height is at whatever height the observer or the values are available for all the different variables. So so the flux gradient relation, so all these basics we already discussed. The fluxes we are expressing in terms of their local gradients multiplied by the eddy transfer coefficients. The main thing is that the local gradients should be available, and the values of these coefficients K. So if the local gradients are not available, then we can rely on the bulk aerodynamic formula. Advantage, as I mentioned, we can use the surface value, and at whatever level the measurement is available above the surface. And at the surface means then, okay, wind at the surface, we can take it as 0. Then we use the wind at only one level, at say 10 meter, the reference level. We can, if at 10 meter level, either the estimate calculated value in the numerical model or observation, the value available at 10 meter, then we can use that U. So that's why we don't see that gradient in the wind here. And then you take the difference. For example, if you are calculating the temperature flux, so take the skin temperature of the surface and the measured value, or the whatever level the value available at a particular height, say 10 meter or 20 meter. And then with this formula, we can calculate this the flux using this bulk aerodynamic method. And momentum flux is basically rho multiplied by U star square. U star is the friction velocity. a scaling velocity, and I think this also will be discussed in the next class. So here again it is u square. So we are basically taking this u and at the surface u is 0. So that's how this results in another u only. So that's how this becomes CD multiplied by u square. So this drag coefficient CD, it is dimensionless, and basically it depends on the roughness of the surface. So and then there are for the heat flux and the moisture flux, similar relations we can use, and there are different drag coefficients available for all those fluxes. Also, in some situations, this may be the CD, the drag coefficient for heat and moisture may be close to the drag coefficient for momentum, but many other situations it will be different also. So this type of formulations are commonly used in weather and climate models. So just to give some understanding, the drag coefficients for different types of surfaces are given here, and the corresponding roughness lengths are also given. Remember that all these values given are for the neutral conditions. Whatever we discussed so far are applicable only for the neutral condition, the K coefficients, Km, Kh, Kq, and all these drag coefficients for momentum, heat, and the moisture. So all what we mentioned so far is applicable for the neutral situations, and how we can calculate the drag coefficient neutral situations are explained, given in these relations. So we can calculate this CD and CH and all that, provided we using the roughness of the survey, aerodynamic roughness length Z0, and the level of our interest. So using that, we can calculate this coefficients and use in those relations typical values of all these coefficients are I have mentioned here. So you can go through that, and if you want to use to calculate this fluxes using the bulk formula. So basically, you can use this type bulk or gradient method. Gradient means that you need measurement at two heights. Bulk means at the surface and at one level above. So this type of simple setups we can make use. We can use the tower measurement also for the and you can use all the mean sensors, which measures basically the mean wind speed, for example, and mean wind speed direction. There are different types of sensors I have shown here, and the air temperature and relative humidity. Again, not the fast high frequency sensors. For the mean measurements of temperature, relative humidity at different heights, and these days people use all these multi-component sensors which can measure the temperature, humidity, rainfall, wind speed, direction, everything all in one. But if you want to use the gradient method, you need to have the measurements at two different heights. So get the measurement, put it in that equation, and use it. So, typically, so the gradient means that you need to have measurements at two heights. Just an example, the air temperature measured at two heights are shown here. So you can calculate the gradient difference between the values of air temperature at two heights or the relative humidity at two heights. We can use, and then we need the information about the wind speed also. So with the help of this, we can calculate the fluxes either using the gradient method or using the bulk transfer method. So now the another issue we need to address is that what if the atmosphere is or the boundary layer is not neutral? So neutral situations we can expect not so often, not very common. So usually neutral conditions are like kind of overcast conditions, totally overcast situations, some of the monsoon conditions, and also windy and overcast situations. We can expect the boundary layer to be neutral, and also during the transition periods, morning hours, very close to sunrise and also very close to sunset. the heating is very weak, and the sufficient wind speed is also there, then also we can expect neutral. But other than this, the atmosphere or the boundary layer is either unstable, nearly weakly unstable, or stable, highly stable, like that. So we should be able to make use of the gradient method as well as the drag method to calculate or estimate the fluxes. The eddy covariance direct method, we don't have to worry. Whatever fluctuations you are getting, you can directly use. No stability correction there. But here, all those coefficients like Km or the drag coefficients, whatever we originally use is meant for neutral conditions. So we have to modify those for the stable and unstable conditions. So we can, so we need to apply the corrections for the stability, means for stable and unstable situations. Commonly followed approach is that to make use of the similarity relations. So that itself is a huge topic to discuss. Some of the important points I have mentioned here, and I'm running out of time also. So I'm not going into the details and the similarity relations. So basically what we are doing is that all those we group the variables, both the dependent and independent variables into groups, and then express that in terms of the stability, saying that in a very, very simple way. So what we want now, our focus is in the surface layer, in the lower part of the boundary layer, and we want to see how it can be applied. The similarity relations can be applied to correct those flux gradient and drag fluxes for different stability conditions. So one commonly used approach is using this similarity relation suggested by two Russian scientists, Monin and Obuko. So according to them, vertical variation of almost all the variables and their fluxes in the surface layer, and after normalizing with the various scaling parameters appropriately, and then they can be expressed in terms of certain other quantities like the momentum flux, the heat flux, the measurement height, and all that. But all these quantities can be grouped and expressed in terms of a single parameter, the stability parameter set by L, which we mentioned previously. So all the quantities, all the variables, their fluxes, and all that we can express as a function of Z by L. So that is what, in a very simple way, this Monin-Obuko similarity relation says. And there are several similarity relations for the gradients in the wind, the gradients in the potential temperature, gradients in the mixing ratio. So here you can see that all of them are expressed. The gradients are expressed in terms of different functions of this stability parameter Z by L. And phi m, the functions are different. Phi m for the momentum, phi h for the heat flux, phi q for the moisture flux, like that. And there are different functional forms which are mentioned here. So Z by L basically gives us the information about the stability changing. So negative stability Z by L in this range, it is unstable. So unstable, the functional form is given by this. And if it is stable, and then we have to use the functional form like this. And that changes from for the momentum to the other heat and moisture fluxes. So we can use this the functions, this similarity functions to correct the eddy transfer coefficients for different stability situations. For example, the Km and Kh, we can correct the stability function multiplied by with this factor. So you will get the stability corrected Km and similarly Kh, like that. And if the frictional velocity and all these the Z by L requires the fast measurements, but we can express in terms of the Richardson number, which requires only the the gradients of the mean values of temperature and wind. So all these corrections we can apply in terms of the Richardson number also. So that way we can correct the wind profile, making use of this similarity function, stability corrected values of the gradients. And from that, we can derive other similarity functions and get the values of CD also. So these are basically the stability corrected similarity, stability corrected drag coefficients for momentum and also for the heat. So this way, we can make use of the flux gradient relations as well as the bulk transfer relations for all stability conditions. For originally it is for neutral, but we can make use of it for the other situations like the stable and unstable as well. Okay. And kind of I can stop here. So what should I do, Professor Somashwar or Dr. Rohini? I stop here or I can.
Sir, you want to continue for another 10?
Maybe I discuss just one more topic.
Yeah,
because
sure.
I think that it is somewhat important for discussing about this surface energy balance. I feel that is I'm missing a lot.
Okay.
So we talked about all this the fluxes. Either you can directly measure using eddy covariance method, using all those high frequency sensors, or you can estimate using gradient method or bulk transfer. And there are other fluxes energy that controls what are happening in the boundary level. We know that the basic source of all the energy is the radiation, the short wave as well as the long wave form. So that is basically what driving everything. So what is absorbed at the surface, heating the surface, and then all this turbulence is generated. So there is conversion of whatever energy is available. So that is what we are going to talk about in this subject topic, surface energy balance. So how much of energy is received at the surface, how that is converted or partitioned into the other forms. So on the left-hand side of this equation, you have the net radiation, which includes the four components of the radiation: the incoming short wave, incoming long wave, reflected short wave, and outgoing long wave. Putting the appropriate signs, the resultant is the net radiation. So that is the available energy basically. And how that is converted, how much of that is converted into sensible heat, how much of that is converted into the latent heat, and a small part of it will be going into the soil also, because if surface is getting heated and the layers below, soil below will be at a cooler temperature. So there is a gradient in temperature. So there will be conduction. The heat will be conducted from surface to the soil levels below also. And during night time, it will be the opposite. Surface cools fast, surface temperature can be cooler than the soil below, and then the transfer of heat will be in the opposite direction. But that has to take place. The ground heat flux is through conduction, but here you know that it is mainly through the convection, through turbulence. So whatever it is, so how the net radiation is partitioned into the other forms of energy. So basically, this surface energy balance decides the surface temperature. So that way, so if you want to model or look at how the surface temperature is changing, then you need to look at the surface energy balance, and basically how much of sensible heat is transferred into the boundary, into the layer above. That basically that has a lot of influence on the boundary layer growth and other processes. How much of what is happening at the surface in terms of energy partitioning, that is very important. So this is just a way of representing all those fluxes during daytime according to the direction of that transfer. So net radiation, the net will be towards the surface, and during daytime, the sensible heat, and if the surface has moisture, there will be evaporation and or evapotranspiration. So flux will be away from surface, and the G will be going to the levels below. And night, it will be the opposite. So the details are mentioned here. So, and then we can assuming that we are using eddy covariance direct measurement, and then we can calculate the energy, the diurnal variation of these different components. Net radiation, we can measure all the components and calculate net radiation, or directly measure also using, there are sensors available which gives net radiation directly. So that way it will give, and then HLE we can using eddy covariance or other methods we can calculate, and G also there are sensors available to measure the soil heat fluxes, and then you can look at how the net radiation is partitioned into other forms. This example is from a month of May, relatively dry period. So you see that most of the net radiation, a major partitioning is into the sensible heat flux. Some amount of latent heat flux also is there. And then the G is relatively small. Then looking at the energy balance, so if there is actually what we expect is that the energy, a certain amount of energy is reaching surface, okay, that it is partitioning into all the other three components and perfect matching. If net radiation is 200 watts per meter square, everything, the other three components together should be 200 watts per meter square. But that is rarely achieved. There are so many issues related to the measurements and so many other physics involved. So always there will be a residual. So if you take the difference between net radiation and other components, then you will see always there is a difference. So that means energy balance is not perfectly achieved. So there can be. So if you achieve close to 80-85%, that is kind of considered as perfect, with all the uncertainties involved in various ways. So if you see that if you net radiation is 100 and all other together say 80-85 watts per meter square, it is considered as kind of good energy balance closure. Different examples from different seasons and all shown here, just to show that all these different components vary with the time. And I will stop with this. This I'm showing from a published paper, an experiment they did in Germany. So they identified a mesoscale grid, or typical size 20 kilometer by 20 kilometer. And so you know that 20 kilometer by 20 kilometer may consist of all different types of surfaces, and they had all this forest, agricultural land, bare soil surface, water bodies like large lakes, bare soil, all kinds of surfaces. And they did measurements of this energy balance, like net radiation, sensible latent heat, and the ground heat flux, everything. All measurements over all different types of surfaces within this 20 kilometer by 20 kilometer. And here they have plotted this just two components. Net radiation could be nearly the same, considering that clear sky conditions, net radiation could be somewhat the same. But you see that if you remember everything within 20 kilometer by 20 kilometer, large difference among this is just the sensible heat flux, but over different surfaces. So large difference. Some surface the values are like 400 watts per meter square, whereas our water bodies it is close to 0, or depending on if it is agricultural field, it is showing say close to 100 watts per meter square, and similar variations over water bodies and forest, agricultural field. The large latent heat and sensible heat is very small. So within a mesoscale grid itself, there is very large variation in the sensible heat flux, latent heat flux. But when it comes to numerical modeling, are we actually resolving these fluxes like that? For a grid or throughout the domain, we will be using some schemes, And okay, we'll be using some soil moisture, temperature, initial conditions and all that. And then we will be estimating all these fluxes. So there is no way that we are resolving all the fluxes as we are seeing in the observations. So, and then of course, you know that if you use that for all the in the simulations, then naturally there is going to be errors. I'm not saying that the errors in the forecast and all that is only because of this, but definitely all these are contributing to that. So correctly representing the fluxes are very important in the numerical models. So with that, I think I stop here. Actually, I have more slides, but I'm not going to. I don't want to trouble you more, so I stop here. So thank you very much for giving this opportunity to me to deliver these 2 lectures on boundary layer methodology. Thank you.
Thank you, sir. Before we go to the question answer session, we would like to have photo session. So I request everyone to please switch on their cameras. Ashwin, can you take picture?
Thank you.
Thank you. So now I request Mrunal Naik from IITM and SPPU also, so to conduct the question answer session.
Thank you, ma'am. Thank you, sir. There is question from Krishna Priya. Thank you, sir, for the informative class. Her question is, if observations are made at 10 meter above the surface, how can we obtain measurements below that height, especially for variables like wind speed?
It's confusing. Measurement at 10-meter height. How do we get information about wind speed?
Below that height. Yeah.
You mean, so maybe what she meant is that the wind speed measurement, actual measurement is at 10 meter, but then we want to estimate the wind speed below 10 meter. Could be, right? I can.
Yes, sir.
Yeah, that is the case. Okay, we have this. Yeah, if it is just the wind speed, yes, we can use the logarithmic wind profile relation, which says the wind at any height u as u star by k logarithm of z by z0. So that is again for the neutral stability. So u is, say for example, her question is what if you want the measurement? No, I mean to estimate the wind at say 5 meter. So u at 5 meter we can calculate using knowing the value of the friction velocity u star and u star by k, which is the von Karman constant 0.4. And multiplied by the logarithm of z by z0. Z is that 5 meter and z0 is the aerodynamic displacement height. So, but z0 and u star should be known for that particular height, which of course we can estimate, but that is required. So if that information is available, then we can use to calculate that wind speed at that height. And yeah, and if it is other stabilities not neutral, then the stability corrections will have to be applied. So that way it is possible, but may not be very accurate and all.
Thank you, sir. So there are no more questions.
Okay.
Maybe we'll go to vote of thanks and candidates will still ask the questions. So
Yes.
I would thank you, Brunal. I now request Ashwin Zadav from SPPU to please give vote of thanks.
Thank you, madam.
I'll share my slide. I hope it's visible.
Yes.
On behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of 24th lecture in our in our weekly online lecture series on atmospheric dynamics and its application to climate sciences. We are especially grateful to Professor Someshwar Das, Secretary SAMA, for his warm welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Professor Anandakumar Karipot, for delivering an enlightening lecture on governing equation for mean flow in the PBL concept of turbulent Eddy. I would like to acknowledge Dr. Rohini Bhavar for moderating the session and Ms. Mrunal Naik for efficiently managing the question and answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members. A special thanks to all the participants and attendees who joined us from across the globe, and to the dedicated team members at Savitribai Phule Pune University for their invaluable role in organizing this lecture. Thank you all.
Thank you, Ashwin. So there are participants, if you have any more questions, you can please ask. Das sir, I would like to know if you have anything, some closing remarks on Tyagi sir and Das sir. Sir, you are muted.
Maybe Tyagi Saab can summarize the piece.
Yeah. Tyagi sir, some closing remarks.
No, it's a great finale for the series of lectures, and especially on the PBL. Thank you, Professor Karipot. And we do acknowledge all our eminent speakers for their contribution and sustained efforts to keep this series going. Also the participants, which I see for last 3-4 lectures, have consistently attended the classes. So that's very encouraging, that interest in the PBL, which is a very important topic. And my request is that if we should bring out the abstract, and of course these lectures are available on YouTube for the benefit of the wider community. We should publicize it also for wider circulation. And the abstract booklet, if it comes out, also will be of great help. And I'm sure the MCQs are not coming also because of the final exam. We need them, and that will be a good, I think, question bank also will be created there. Thank you, Rohini and the team. And of course, thanks a lot to Dr. Anandakumar Karipot for his lecture. Normally, you see, people after 30-40 minutes switch off, but your lectures were so interesting that you covered very, very nicely. Thank you so much.
Thank you, sir.
Thank you, sir. So 2 announcements for the participants. All the study material provided by various speakers is given in a link. We had shared the link with you. On Monday, I will share it again, but on WhatsApp, I have shared it multiple times. So please go through the link, and whatever new like today's lecture, we will receive the PPT and presentations. We will be sharing it. We'll be putting in the same link. So you will have the updated link. So you will have everything in that same link, all the study material. And the exam will be conducted on 26th of July, same time, 3-2. So we will circulate an email regarding that also. So please try to watch all the YouTube, revise and watch all the YouTube videos, and best of luck for the lecture, for the exam. Das sir?
Yeah, it was great lecture series. In fact, it is the longest lecture series that so far we have conducted on 5 different subjects. And this is 24th lecture, one more lecture. There are some more than 6 months. This lecture series has continued. And especially thanks to the Pune University, because Pune University is the host for this lecture series. And both Dr. Rohini as well as Dr. Anandakumar Karipot, both belong to the same university. So thanks a lot for your great support and contributions. And lectures were quite interesting. Of course, BBL is so important. And the last question was also quite interesting. That Krishna Priya or somebody asked, saying that if the wind measurements are done at 10-meter height, then how to estimate the fluxes below 10 meters is quite interesting. But the height of the surface layer itself is 10 meters. And so if you want something within the surface layer, how to do that? It's quite interesting. Well, I mean, I already explained by Professor Anand Kumar that we can estimate certain characteristics using the logarithmic law profile of the surface layer, and we need certain things like von Karman constants and other things already explained by Professor Anand Kumar. But it's a quite interesting question. And within the surface layer, if you want something, you can also have the curiosity. Maybe you can just move around from the bottom to the top of your building. And if it is a multi-story building, you can move around with a handheld instrument, right? And then try to measure the fluxes. If you are so curious. But then, yes, boundary layer towers are available. 50 meters tower, but that is 50 meters, not. And one can fit in the instruments at lower levels also. Although there are so many things like there are obstacles, the trees, the buildings, and all those things, can hamper the real situation. So the real fluxes will be difficult for the wind, especially for temperatures and moisture. I think there is no problem because any temperature is measured at 2-meter height from the Stevenson screen and as well as from other instruments. So temperature, moisture, there is no problem. Fluxes of that can be obtained. But for wind, of course, the standard method is for 10 meters, and that is done because of the obstacles, to avoid the obstacles of the buildings and then the trees and other things. So anyway, good question, and thanks for explaining so nicely, Professor Anandakumar, the question. So thank you so much. It was quite interesting session once again. And one more lecture is also focusing on the boundary layer itself by Professor C. A. Babu. So we'll have 3 lectures and plus one very inaugural lecture by Professor P. N. Sen on the applications of the PBL on the pollution transport and so on. So we have covered 4 lectures almost on the PBL, which is such an important topic. So this is very good. Thank you very much once again. And over to you, Dr. Rohini.
Thank you, sir.
Thank you, sir.